So any questions on PA3 or other stuff?
I've forgotten which way we're supposed to get the hash function. Are we supposed to, is there a file in temp that we're supposed to copy?
There's a /temp/database.txt that you can use as a test file.
Okay, but are we supposed to transcribe the hash function into it being a function?
So the hash function is this thing that takes a string and adds up the ASCII codes multiplied by the position plus 5, and then reduces modulo the hash table size. That's a function you're going to write. Takes a string, gives you an integer. The thing in /temp database txt, that's just a sample file you can play with.
Okay.
But
Let's just see if there was a temp hash function.
No, you gotta write that.
Telling you that I do need to write it.
Yeah, you gotta write that.
Myself is a.
Yeah, and just code it. Just code up that
up.
formula with the summation
Okay.
in the assignment write-up. All right, so let me talk a little bit more about this global variable business. So I suggested yesterday putting all of your hash functions into a single hash.c, okay? Partly to simplify your make files, partly to simplify your own life when you're trying to edit things, partly because your hash functions are mostly a few lines of code. They're really wrappers around your list functions. Your hash init is a one-line for loop. Your hash add is a one-line function, right? If you squeeze everything together. So you don't really need those to be in separate .c files, but it also simplifies this global hash size variable if everything's in one hash.c, because you just declare the hash size in the very beginning. All your hash functions can get to it. If you want to have your hash function split into separate files, though, you can still use this global by using this extern keyword. So I just made some sample code to show you how to do that. Here's a main program, and it has two functions it's going to use, save and retrieve. Save will let me save an integer value into this global variable, and retrieve will read that global variable and print out its value. Okay, so this is like, calling hash init with a 10, and then I want to be able to read that value later on. So the save function, there's my global variable. It's declared outside of any function, so it's global within this file. And any other function I wrote in this file could use the variable save me. Okay, but another file, if it tries to access the variable save me, is going to say save me is not declared. And if I declare save me in another file, it's not the same save me as this. So here's how you do this. Declare what looks like a global variable, but put the keyword extern in front of it. And that says save me as an integer. It's available at any point throughout this file, but it's declared somewhere else. Okay? And that extern will tell the compiler, don't set up storage in here for save me. Wait until we link this file together with other files and find somewhere where something has declared a global named save me. That's the save me I want. So now in my retrieve function, when I say return save me, it's returning the value of that save me up at the top, which is actually this save me from save, which got saved when you called save. Can I say save any more times?
What does extern skip through?
It's not really allocating. I mean, it's pointing to a variable, and all your variables they go away when your program exits. So basically when you exit. And if you want to be old school, you can say static, but I don't think you do that anymore. But static meant don't go away. But I don't think that's a thing anymore. So if we compile this and we run it, the machine is slow. If we run it, it gets back that value. That value it printed out came from this call to retrieve, which read the value that was declared in another file. So you can set up your globals across multiple files like that. But I still think it's cleanest to just have one hash.c file with all your hash code in it. But either way. All right, other questions? All right, so I said I was going to talk about queues today. I'm not. I'm going to talk about queues later on. I want to start talking about trees because I think we have really good momentum going with lists and data structures and pointers and dereferencing, and you're hopefully deep in PA3, so you're thinking data structures and lists. And this is really a good mindset with which to move on to binary trees. And trees are probably the most common data structure you'll encounter. There's a lot of different versions of trees, but they're sort of one of the more generally useful structures. Most of what we do the rest of this course and a lot of 223 will be built around trees. A lot of what you do on the job is built around trees. They're good for searching and storing and retrieving and organizing and all kinds of things. And trees are really an embellishment on a linked list. So I want to start by looking at where we are, why we spent so much time talking about linked lists at all, and how we started off talking about linked lists. And it had to do with thinking about order of complexity, how long it takes to do different things. So let me make a bit of a table, starting with an unsorted array. And let's think about insert. And so if we have just a plain array of numbers, not in any particular order, and we want to add one more number to this collection of numbers, it doesn't take long, right? If our array has 17 things in it, we just store our new number at the 18th spot in that array. Array bracket length equals new number, increment length. Doesn't matter if we're putting in the 17th or the 17 millionth place, just copy it into that spot, increment the length. So this is what we were calling order one, a fixed amount of time. Okay, fixed amount of time is the ideal. We'd like to have something that doesn't matter how much data we have, it always takes the same amount of time to do. Similarly, if we want to delete from an unsorted array, and this is assuming once you know what to delete. Like you want to delete element 10 from an array. That's also a fixed amount of time. Because the quick way to delete element 10 from an array is just to take the last element in the array and move that up to element 10. And then subtract 1 from whatever variable tells you how many things are in the array, and you've deleted element 10. So this is order 1. And we can do that because the array is unsorted. So moving this thing from the end to the middle doesn't hurt us. Okay, the real downside is search. If you want to try to find a piece of number in your array, and your array has n elements, this will generally take us around n operations, n over 2, but it's linear. Double the size of the array, double the search time. Because the only way you can search an unsorted array is to check every single element. And if you have twice as many elements, on average, it's going to take you twice as long to search all of them. So unsorted array, quick to insert, quick to delete, really bad to search. So one thing we learn, maybe in 224, is if we have a sorted array, where we keep, say, all the numbers from smallest to largest, we can do a little better on some of these. So if we want to insert into a sorted array, we can't just put something at the end anymore, unless it happens to be the biggest. Usually it's going to go somewhere in the middle, and the only way we can do that is to move everything else down one spot. If there's n things you have to move down, it takes n operations. So inserting in here goes to order n. And deleting, unless you want to have holes in your array, is also order n, because to get rid of an element in the middle, you've got to move everything up. We can't just take the last element and fill in that hole, because now our array is not sorted anymore. So insert and delete have gotten really expensive, but search is improved. So what's the efficient way to search a sorted list of numbers? Exactly like the high-low game. That's what high-low is. You're searching for the number that this person has in their head, right? And you know it's somewhere between 1 and 100. So with a sorted array, you go to the number in the middle, right? You can do that, order 1, and you say, is this number bigger or smaller than what I'm looking for? If that number in the middle is bigger than what you're looking for, you can ignore that second half of the array, because everything in there is going to be bigger than that number in the middle, which is bigger than what you're looking for. Don't have to consider that half. Boom, your problem just got cut in half. You had 1 million numbers, now you've only got 500,000 numbers to search. One operation is all it took to get there. Now you got 500,000 numbers, look at the number right in the middle. Hey, that's smaller than what I want. I can ignore the first half of that new array. Just look at the second half, now I've got 250,000 numbers. 2 operations, my problem is 1/4 as big as it was. I've gone from having to search 1 million to having to search 250,000. Every single operation you make cuts your problem in half. Okay, how many times can you cut something in half until you get down to 1? That's basically the log of n. It's log base 2. Usually when we write log in computer science, we mean log base 2, because we're so binary centric. Log n is nice. Log n operation means if you have 1 billion numbers that you want to search, you can complete your search in about 30 operations. Because if you cut 1 billion in half 30 times, you end up with 1. And to search an array of 1 element takes 1 operation. Just check the 1 element. So this is a really good time efficiency. Very fast to search a sorted array, but inserting and deleting have gone to the dogs. Now sometimes that's okay. Sometimes you're just going to insert a bunch of stuff into your array in the beginning of some function, and then for the next year you just want to search. Okay? A database of phone numbers would be like this. You don't insert, 1 million new phone numbers every day. You have to insert in the beginning to build your database, but then, once in a while a new phone number comes in or a phone number goes out of service, you do an insert or delete, but mostly you're searching. So for that kind of setup, sorted array works great. But if you want to do a lot of inserts and deletes, this is pretty poor performance. Okay, order n is expensive. 1 billion things takes you 1 billion operations to insert. So to deal with that, we started talking about linked lists. And a linked list, the idea was if we know where we want to insert, right, so assuming we know where we want to insert, we don't have to move everything down in memory. We can put a new node right here and just point to it from the thing before, point to the thing after. It's a fixed amount of operations. So linked list, our insert goes back to order 1 and our delete goes back to order 1, assuming you know where you want to delete from. Now, for our code, we still had to search to find the node we want to delete. But if someone says, here's a pointer to the node you want to delete, it's a fixed amount of time. Okay, but the search goes back to order n. So seemingly, this is no better than an unsorted array. But the thing about a linked list like this is it can be sorted. And the insertion and deletion are still order 1. Okay, and we have some sense that if we sort our data, we may be more efficient at searching it. Data with some kind of organization, there's a good chance we can search it better than just a random pile of numbers, right? So we're trying to get to something like this for search efficiency, but still keep these efficient inserts and deletes. Something better than n at least, because order n, usually not what you want. Order n squared, even worse. But if we can do better than order n. Okay, so we're going to try to combine these. And I want to look at the search in particular. Okay, sorted data, we search by playing high-low. Pick a number in the middle, use that to decide which half of the array you want to search in, and keep going like that. With a linked list, we don't have a direct way to do that. So there's a linked list of 7 numbers. It's sorted. If I want to find the number 60, I start here, I move along. Hey, there's my 60. Okay, order N. Now to do high-low on a linked list, what do I need to do? First thing I need to do is I need to start with the number in the middle of the list. Well, how do I find a number in the middle of the list? Well, I have to know how big the list is. Divide by 2, move over that many nodes. There goes my efficiency. So here's what we're going to do. First of all, we're not going to have sentinels anymore. Okay? We're going to forget about sentinels. And our list is going to be, you know, something that gets us to our first node. Well, instead of starting at the first node, we're going to have something that points to that node right in the middle of the list. So now if we want to find the middle, it takes one operation. Hey, just have this thing which I'm going to call root. Root arrow data, that's the data value in the middle of our list. All right, so that's our first divide and conquer. That's where we make our first guess. Check the number in the middle of the list. Here's the trick. Suppose that 40 is too small. Suppose I'm looking for the number 50. Okay, 40 is too small. I know my number cannot be in any of these things to the left of the root. My number is somewhere in this smaller linked list, which is half as big. Okay, how am I going to search this efficiently? I need to start with a number in the middle if I'm going to keep doing this high-low game. So once I've decided that I only care about the list at the right, I need a way to get to the list in the middle, the node in the middle of that list. So I'm going to put a pointer right here, which points to the middle of that sublist. And in case 40 was bigger than the number I was looking for, I need to search this left sublist. I need something that points to the middle node of that. I'm going to put another pointer on that root node, which points to the middle of the sublist on the left.
So how do we know that our root node is exactly right?
Is exactly what?
Is exactly
You got to trust me. Right, so if this is the list, right, I will give you a pointer to that node in the middle. Okay, we're going to ensure that that happens by how we construct these things eventually. Okay, well once I get to the 60, if that's too small, then I need to search the sublist on the right. It's only one number, but it could be, you know, a big long list of numbers. Same thing, I need something that points to the middle of that list. And I need something that points to the middle of the sublist on the left. And same thing if I went to the 20. And so this is a different kind of linked list. I have a starting point that's in the middle instead of the beginning. And I have 2 pointers, 2 arrows coming off of each node. One pointing somewhere on the left, one pointing somewhere on the right. Okay, this is a binary tree. And so let me draw this slightly differently. So I'm going to draw the root up here at the top. And this arrow that goes to the left, I'm just going to draw as a line, and we're going to put the 20 that it points to. And the arrow to the right, I'll draw as a line slanted to the right, and I'll put the node it points to. And now the 60 has a node on the left, which is 50, and a node on the right, 70. And the 20 has a node on the left, 10, and a node on the right, 30. And this is the typical way we would draw a binary tree. And there's a few things going on. First of all, this number at the top, which we can call the root, this is the thing that we use to get to the tree. Okay, that's the thing that we have some variable that points to. So everything we do with the tree, we do through the root. It's what we can think of as a handle to this structure. Okay, every structure has a handle. For a linked list, it's a sentinel node. For a hash table, it's the location of the first element in the array. For a tree, it's the address of the root. Yeah?
So when you think about like a pointer to the tree or not?
Yeah, basically. But again, this idea of a pointer to a node versus the node itself is a little slippery. So we usually think of the root as this node containing the 40 rather than a pointer to it. But when we implement this, it's going to be a pointer to a struct node, where the struct node is, something that contains a 40. All right, we don't usually draw arrows. We simply assume that when we draw something going down to the left or the right, that there's an arrow pointing in that direction. But we don't usually draw the arrows themselves. We also assume that when there's no arrow coming off, there's actually an arrow that points to null, just like at the end of a linked list. But when we draw a list, we don't usually put in that last node that says null that it points to, right? We just understand that you're at the end. If you look at the next field, its value is null. So we don't usually list those. All right, so here's a binary tree. And this is actually what we call a binary search tree, or a BST. But the reason it's a binary search tree, beyond being just a binary tree, we'll get to in a few minutes. Let's just think about binary trees for a minute. Binary meaning that each node has at most 2 nodes that it points to. Now this is still a binary tree. The 10 is pointing to a 5 on the left. Technically it's pointing to a null on the right. Okay, it has 2 children, but one of them is null. So we kind of think that it only has one thing that is pointing to the 5. Okay, but we don't allow the 10 to point to a third thing, for example, or the 40 to point to 3 things or 4 things. That would be a tree, but not a binary tree. So binary, you can point to 2 things, or 1 thing, or no things. All right, and we draw the root on top, but it's kind of an upside down tree, because usually the roots are at the bottom on the ground, and then as things go up they branch out and get very full and wide, right? So the trees we draw in computer science are always upside down. There's a bad joke in there somewhere. All right, so still with me? All right, so we need some terminology. So let me draw a clean picture of a tree. Alright, that's a perfectly fine binary tree. And it's actually a binary search tree. So this node on the top, we call that the root. When a node, and we call these things nodes, right? They'll be like struct nodes in C. So when a node points to another node, right? The thing it points to we can consider to be a child of the thing that points to it. So 60 is a child of 40, and 20 is also a child of 40. So we think of it like an ancestry tree. And we call 40 the parent of 20 and also the parent of 60. And so every node has at most 2 children. Yes?
So does that trickle down all the way to the bottom?
That trickles all the way down to the bottom. So 45 is the parent of 47, and 47 is a child of 45. 47 is technically a grandchild of 50, and a great-grandchild of 60, and a great-great-grandchild of 40. We talk about grandparents and grandchildren sometimes in some of our algorithms. I haven't seen ones that go beyond that, but sometimes you need to go up 2 levels in the tree. And we'll talk about siblings. We can call 20 and 60 siblings because they share the same parent. And we can talk about nieces and nephews and aunts and uncles. And those come up in some algorithms. But for now, just parent and child. And not every node has children. 80 has no children. Every node has a parent except for the root. The root has no parent, but every other node in here has a parent. And it has exactly one parent. So this kind of makes some sense maybe. All right. A node with no children is called a leaf. In a tree, every branch has more branches coming off of it until you get to a leaf, and then the leaf has nothing else coming off of it. In a simplified view. So a node with no children is called a leaf. The root is the node with no parent. Every other node has a parent. And if you follow the path from a node to its parent, to that node's parent, to that node's parent, and keep going, eventually you will get to the root. Right? 7's parent is 5, parent of 5 is 10, parent of 10 is 20, parent of 20 is 40, the root. And if you start from the root, you can follow a lineage of children to get you to any node. So from 40, I can go to 60, 50, 45, 47, and get to that node. And it's useful when we draw these pictures to sometimes talk about left and right children. So 20 is the left child of 40, 60 is the right child of 40. And that distinction gets to be important. Okay, and then a few things to note about binary trees. Everything is connected. If I have a node sitting over here that's not connected to something else, that's a separate tree. It's not part of this tree, right? That would constitute a family of trees, which obviously we call a forest, and we talk about forests sometimes. But in a single tree, everything has to be connected to some other part of the tree. So we can't break away this link and say, hey, here's my tree, right? Nope, this is not part of that tree. We've got two trees. And you can kind of tell that's true because if I consider this whole thing to be a tree, well, this node would have no parents, right? And this node has no parents. It's like I have two roots. Okay, so everything has to be connected. Each node has at most one parent. The root has no parents. Every other node has exactly one parent, which means I don't want a node from 10 up to, say, 60 over here, where 10 would have two parents, 20 and 60. That's not a binary tree anymore. Also, we have no cycles. So I don't want 47, for example, to be the parent of 40, right? So if I were to draw a line from here up to 40, it's no longer a tree. And you can tell that because there's a cycle in here. Now it's still a data structure. It's a structure called a graph, which we'll probably get to at the end of the course. But it's not a tree. So no cycles. Root has no parent. Every other node has exactly one parent. Everything has to be connected. And you have less than or equal to 2 children per node. That's the binary part. So that's a binary tree. There's an additional property for a binary search tree. in a binary search tree, if we look at any node in the tree, like the root, for example, everything to the left of that is going to be smaller than the root's value. And everything to the right is going to be bigger than the root's value. So everything I find over here is going to be smaller than 40. And everything I find over here is going to be bigger than 40. And that's got to be true for every single node in the tree. So if I look at my 60 right here, everything to the left is smaller than 60, everything to the right is bigger than 60. Okay, that property is what makes it a binary search tree. So for any node n, all nodes to the left of n are smaller and all nodes to the right of n are larger. And these are struct nodes, so they have, you know, in this case, an integer data field and a left pointer and a right pointer. When I talk about the value of a node, I'm talking about the value of the data field, okay, which I'm just drawing with a number here. So any node that I pick, 20, everything to the left is smaller, everything to the right is larger. If I pick a leaf node, there is nothing to the left or the right, so that satisfies this property in the sort of empty sense. Okay, still good? All right, here's the magic. So there's an arbitrary binary search tree. The whole thing is a binary search tree, right? I can pick a node like the root, and I can look at everything to the left. And I can look at everything to the right. Well, guess what? This thing that I circled in green, this is a binary search tree. It's got a root of 20, which has no parents. Every other node has exactly one parent. Every node has at most 2 children. And anywhere in this tree, if I pick a node, everything to the left is smaller, everything to the right is larger. That's a binary search tree. And guess what? This is another binary search tree. So my tree is composed of a pair of binary search trees, which are the children of the root. And hey, you know where I'm going with this. If I look at this tree that I've circled in green, and I think of this as the root, if I look at the thing on the left and I look at the thing on the right, those are binary search trees. Your induction neurons should start flickering around this time. Because we're going to make statements about binary search trees, and we're going to prove things about binary search trees by proving things about binary search trees. Right? We'll make a statement about binary search trees that have this much stuff, and then we'll use that to prove things about binary search trees that have a little more stuff. And we'll use that to prove things about binary search trees that have even more stuff, and eventually we'll use that in inductive proof and prove something about all binary search trees. The cool thing about this, though, is we're not just going to prove things about binary search trees, we're going to implement algorithms for working with binary search trees by implementing algorithms that work with binary search trees. So how are we going to search one of these trees for a piece of data? We're going to write a function called search. And what's that function going to do? It's going to use a function called search. And we're not going to really have to write more than like 1 or 2 lines of code to do most of everything we want to do on a search tree. So that's coming in another day or two, and it's going to be our full-on foray into recursive programming, which once you've done recursive programming, your world is changed forever, for better or worse. Usually for better. It's just a very different but really, really powerful way to think about programming. And this is like the quintessential structure to build that understanding around. All right, so a bit more terminology. So this is the root. We know these things that have no children are called leaves. We can talk about the depth of a node. So let's look at this 80 right here. The depth equals the number of hops, or links, from the root. So start at the root. How many things do we have to travel to get to this node? 1, 2. So this node has a depth of 2. How many hops do we have to follow to get to the 75? 1, 2, 3. 75 has a depth of 3. The 90 will also have a depth of 3. From the 40, the root, we go 1, 2, 3. We get to the 90. And if I draw this very carefully, right, everything here is going to have a depth of 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. So depth is you know, sort of literally how deep you go down this picture to get to your node. Everything up here has a depth of 1. Because from the root I have to travel through one link to get to that. And the root has a depth of 0. Because you don't have to travel any distance to get to the root from the root. So nodes have a depth, okay? Trees have a height. So the height of a tree equals the maximum depth of its nodes. So it's the depth of the deepest node, which I think is this 24 down here, which has a depth of 1, 2, 3, 4, 5. Whereas these have a depth of 3, 3. So this is the deepest node, its depth is 5. The height of the entire tree is 5. Okay, so it's how deep the tree is, basically. If I have a tree with just a root, what's its height going to be? How many nodes are there in this tree?
Well, there's only a root.
There's only one node.
A depth of 0, so it has nothing but the root.
Mm-hmm. So there's only one node, which is the root. The root has a depth of 0, so that's the deepest node, so the height of this tree is 0. Okay? Slightly counterintuitive because it has, you know, it looks like it has some height. I can see one node sitting up there. But technically, the height of a tree containing just a root is 0. Okay, there's no sentinel nodes from here on out. So if we have an empty tree, it's really just null. If we have a struct node star called root, and we want root to represent an empty tree, we set root equal to null. Okay, so what is the height of an empty tree? It's not 0 because we don't have any nodes in there. The height of an empty tree is actually -1. And that's fairly nonsensical, but it's a definition, and it makes all the math work out really nicely. So we live with that. It's like 0 factorial equals 1. Well, that makes no sense by multiplying integers, but it makes things work out. So the height of an empty tree will be -1. The height of a tree just containing a root will be 0. And we'll say that again when we start talking about coding up height algorithms. Yeah.
So for an empty, no root, no node.
No root, no nothing, right? And for an empty list, what we mean is we have a sentinel node that points to null. For an empty tree, what we mean is there's nothing, right? If we have struct node star root, if we set it equal to null, that's an empty tree. And if we were to pass that to a height function, we'd like it to give us back -1. other questions? So, yeah, I don't know what it would be. Graphs are a general notion where you have nodes or vertices connected to each other. And in general, there's no restriction on those connections. And that's a branch called graph theory. And it probably predates trees, I would guess. And so trees are really a particular type of graph where we don't have cycles, and we have a few other, but I don't know where the term graph comes from, actually. Yeah.
So wouldn't the search efficiency be based on when the nodes are put into the tree? Because like here we have 40 as our root, and then we get a number like 20, and we say it's less than, so we're gonna point to it to the left. But then if we get like 21, then we'd go to 20, and then we'd say it's greater than, so then it would be 21, so then we could just get like 21, 22, 23.
Yeah.
And just be a slice to the right. So our
Absolutely. So this was the next topic. Is that a binary search tree?
Technically,
Technically, it is. Absolutely. It has a root. Every node has at most 2 children. Things always go in this direction. There's no cycles. Everything's connected. That's a binary search tree. This is the root. And if we pick any point in here, everything to the left is smaller, everything to the right is bigger. Yeah, that's a fine BST. It's also a linked list. And doing anything on this is as bad as doing it on a linked list. So technically this is a binary search tree, but it's not a very well balanced tree, right? If you pay someone to come out and trim your trees and you come home and you see this sticking out of the ground, you're gonna want your money back, right? What you want is a tree that's kind of nice and fluffy and full, something that looks kind of like this, where it sort of branches out and grows smoothly as you go further from the root and so on. So there's a notion of balance. And balance basically says, you know, the stuff on the left and the stuff on the right should be about the same. This is extremely unbalanced. Everything is hanging to the right. If I go down here, everything is hanging to the right, right? This is also unbalanced, even though it looks like, you know, the left and the right are symmetric. Once I start looking at this subtree, right, this is really unbalanced because everything is off to the left, nothing's off to the right. So this will technically be almost as badly balanced as this, okay? And the worse a tree is balanced, the worse our performance in dealing with it. The more balanced, the closer we get to that log n performance. And the intuitive notion of balance is we want things to be filled in at these lower heights, these lower levels, before we start moving down to deeper parts of the tree. So, I mean, we could have had some stuff sitting here, and here, and here, and here, and here, and so on, and we didn't take advantage of those spots. So a well-balanced tree, we would like to fill it in across before we move down. So we will, in a few weeks, talk about how when we're building a tree, we can try to keep it balanced so we don't end up with this, even if our numbers happen to come in this order. Right, so we'll study balanced trees, AVL trees, red-black trees. There's a whole bunch of science around that. And we'll talk about what balance means more precisely. All right, so tomorrow what I want to start with is why do we care about this? What do we do with these trees? How do we get our data out in sorted order? How do we search for things in here and so on and so forth? So we'll start with that tomorrow.